Welcome to this tutorial on the CryoGrid community model, which is a permafrost and glacier model published here in Geoscientific Model Development. And today I will show you how to download the source code, how to install the model, and how to run a few simple examples. So to get the source code, we have to go to GitHub. So this is github.com. And then this is CryoGrid, and then another time CryoGrid, both with a capital G. And this takes you directly to the source code, CryoGrid community source. And this we download simply on the green button here, code, and then download a zip. And in order to run it, we need a second one. You can read here under getting started, both CryoGrid community source. This is the one we just downloaded. And CryoGrid community run are required. So we click on CryoGrid community run. This takes us here, CryoGrid community run. And then once again, code and download zip. If I now go to my downloads, you can see that it has downloaded CryoGrid community run master and CryoGrid community source master. On the other one, we'll come back to this one. And so I just extract both of them. And then I have prepared a folder, which I have called CryoGrid demonstration, where I will do the entire installation. And in here, we will need 4 folders. And I will do them manually. First one is called CryoGrid community source. And the second one will be CryoGrid community run. And you have guessed correctly, you have to be careful with the typos. You have guessed correctly that this is the folders where we will put the source and the master. So when we go to run, we just copy everything that is in there and then go to run and paste it. And we do the same with the source. And then we need 2 more folders. So the first one is CryoGrid community forcing. This is where the model forcing data will go. And then the second one, CryoGrid community results. This is where your use cases, the parameter files describing the model settings, as well as the final model results will go. And we recommend this kind of setup here. Variations are possible, but for the first steps, you should do this. And so while run and source is always the same, this is the code from GitHub. In forcing and results, your cases, your applications will go. So this is your job to populate those. And I have downloaded from the link provided below this one here called CryoGrid simple examples. This is another zip file which I can extract. And when I go in here, you see exactly that there is these 2 folders, CryoGrid community forcing and CryoGrid community results. So I can copy them here. And when you go into forcing, you will see 2 forcing files, one for Ny-Ålesund on Svalbard and one for Juvashø in the mountains of southern Norway. And in the results, there is now 2 use cases, which we will go through today, ground simple and groundwater balance. I will come back to this. Furthermore, there's some plot scripts, which you can also take and copy, for example, into CryoGrid community run. This is just some scripts for visualization, which have nothing to do with the actual model, but we will use them later for the visualizations. So with this, the model is now set up, and I will have to open MATLAB. So now MATLAB is open, and I am exactly in this folder that I made, CryoGrid demonstration. And in order to run the model, I need to go into CryoGrid community run. And then the main file to run is runcg. When we open runcg, you see a user modified part and then a part which should not be changed. And here in this part, I will not go into details for the first tutorial. The most important one is here, this variable run name. And this is where we will now determine which of the runs we want to perform first. So this relates to the folders provided in here. So now I want to run the first one, which is called Ground Simple. I will come back to what is in those folders later. So I go back and I replace this reference run by Ground Simple. If I wanted to do the second example, groundwater balance, I would have to put groundwater balance in here, and then I save this, leave it, and go back to CryoGrid community run, where the runcg is located, and then I simply type runcg, and then the run is actually starting. And now you see here Ground Simple, and then the first simulations are starting. And so this is the timestamps of the simulation. You can see I want to start 1st of September in the year 2000. And so we have now run this. So now we go fast forward in time, and I have just interrupted the runs here. But when I now go into results, Ground Simple, so I've now run it for 10 years, and you see those output files. They first of all have the name of the run, Ground Simple, and then I have selected a certain class which outputs temperature and water and ice contents. And the run I have now done is for a bedrock surface. And you see individual years, so this is 2001 to 2010. And then it has been saved on 1st of September, 0901 of each of the respective years. And so I can now, first of all, clear my workspace. And then I open one of those files. So here you see a variable called out T water ice, which is a structure containing 7 fields. This is now, first of all, the temperature T, capital T, then it is the water content, the ice content, and then the water plus ice content. In addition, it also contains some depth. And I can now make a relatively simple color plot. So just to demonstrate, I can now go back to CryoGrid community run. This is where these CG color plots come handy. So I can now, when I have opened this file, call CG color plot. And then I want the variable here, out T water ice. And then here you have to be careful. This is actually like a character array. So now I want to plot temperature. And I just go for this. And this is my resulting color plot. You can see here for that year, this was the year 2010, I plot the temperatures, which range from -25 to around +15 degrees. You can see the surface here is at the 25. This is meters above sea level. I have told the simulation in the parameter file, we'll come back to that, that the surface elevation should be 25 meters. So this goes to a depth of 5 meters below and 1.5 meters above. So this is the seasonal snow cover that is built up. And you can see here in black, this is the 0 degree line. This is actually the simulated progression of the seasonal thaw layer. And this is for the final modeling here that we have made. So you can see here for this case, this is bedrock. My active layer or my seasonal thaw layer is about 4.5 meters. I can do the same for example, water contents, ice contents. So I can put ice here. What you will see then is, well, the water and ice content inside my bedrock is fairly low. So that's why we have those low numbers. You can see here, the axis goes all the way to 1, from 0 to 1. And so the ice content in the snow cover is significantly higher. So this, of course, relates to our snow density. When I check values here, you can see that this is a volumetric ice content of something like 0.21. So snow density is a little bit above 200 kilograms per cubic meter. You also see here that a bottom ice layer has formed. This is significantly higher densities. And at the very end of the season, you see that this is almost entirely ice. So same for the water. Here it's less interesting. So I can type water here. Well, this is really uninteresting. You can see that the water content in the bedrock is very low. I have set the porosity to be just something like 3%. So you see that this corresponds exactly to the active layer progression. Higher water contents going all the way almost to 1 are only during melt events in the snow cover. So this is the first example. And now the question is actually, how and why does the model do that? What do I now have to do in order to change the model behavior? And so for this, we have to take a look into our CryoGrid demonstration and what's actually going on here. And I go into the ground simple. And what you can see here is that I have the output files. This is the ones that we've just clicked on. But then I have two, in this case, Excel files, which are used to determine the model behavior. So the first one is called constants Excel. Here you can see that we give it physical constants. So this is usually constant from run to run. We just copy that file, but you can see things like the number of seconds in a day, the density of water, the volumetric latent heat of fusion for the freezing process of water, etc., etc. So this is not so interesting. We usually don't change it. But the most important one is now this one. This has exactly, and this is important, it has exactly the same name, ground simple, as the folder. So this here is in ground simple, CryoGrid community results, ground simple. And if you remember correctly, this is exactly the run name in the file run.cg, which we have changed. So how does this file now look like? And here we have the possibilities to determine the entire behavior of the model. And I will not go into very much detail what each of those parameters means, but I will show you how to make a couple simple changes. So a few things that we have told it here. So for example, the altitude, 25 meters. This is exactly the 25 you see here in the MATLAB. So this is the surface altitude where we are. This is the only thing that is interesting here. Here in this class forcing SCB, I have set the file name to be nyolesund.mat. I can make this in red. You can just determine that here. And when I now go back into CryoGrid community forcing, you can see that there is a file called newolesund.mud. This is exactly the file that contains these forcing data. So here I tell it my forcing data are in CryoGrid community forcing, and then it is the forcing file newolesund.mud. Same thing here for the start and the end time. So here I have told it start on the 1st of September in the year 2000. Go back to MATLAB. And we can go back to where it started, and you can see this is where I typed run ZG, and it started on 1st of September in the year 2000. So this is exactly as long as it went. And if I do not interrupt the simulations, they go all the way until 1st of September in the year 2019. Few more things here. I can set a tag to the out files here. This is where I determine my the behavior of my out files. So for example, I can put upper elevation 26.5 and lower elevation 20 meters. This is exactly what we get here. You can see that we go from 20 meters, this is 5 meters below the surface, to 26.5 meters. So this is where I have determined that. And my output time step here, this is days, so this is a quarter of a day. So we have 6 hourly time steps of our output. Also the save dates here, I tell it I want to save it on the 1st of September of each year. A couple more things like the model grid. We'll come back to this. This determines the model physics. And here, this is exactly where I have put a stratigraphy of my subsurface properties. So here in this class called strat layers, I can put in my subsurface stratigraphy. And here I have told it that the entire model domain from depth below the surface 0 meters, so this means from the surface, should have the properties of bedrock. Here I put volumetric contents of water plus ice, mineral and organic. And so this is bedrock because I have told it 97% should be mineral and 3% only should be water ice. I can go back here. This is my ice content. Yeah, in the winter, everything is frozen. So I can click into here. And you can see my ice content, my numbers here is exactly 0.03. If I go to the summer and I do the same, I click in here. This is my water content now. This is 0.03. So this is exactly these numbers that I actually told it here. I also tell it the initial temperature profile, and this I don't provide as a layer. So this here is just like a single layer, but I provide as interpolations between different depths. So here I have told it start with 2 degrees Celsius at the surface. At 1.5 meters below the surface, the temperatures should be 0. And then at 10 meter depth, it should be -2 degrees. And then at 5,000 meters, this is way below our model domain. But I've basically set some relatively warm temperature here. This does not affect the simulations too much. The next thing here is, what are we actually simulating? How are we simulating it? And this comes down to the so-called stratigraphy classes. You can go to the article in Geoscientific Model Development and read some more here. But in any case, I have used this class, Ground Free Water SEB Snow. So this is a class that uses the surface energy balance as the upper boundary condition. It does not account for unfrozen water at sub-zero temperature. So all of my water freezes like free water at 0 degrees. This is the ground free water here. And then it also is compatible with a snow cover, and it does not really have like a water balance. And if you go above here, this is actually what I have chosen in this class called Strat classes. So here I tell it below 0 meters below the surface. So basically, from the surface, use this class ground free water SCB snow, which is exactly detailed later. I've also told it which snow class to use. So snow crocus bucket W SCB. You can read about this class in the publication. So this is what I have done as a user, and you can see a bit the principle here, that the information to run the model is very much distributed throughout this file, and this relates to the different parts of the CryoGrid community model. So essentially, each of the different categories, for example, how do we provide the model forcing, has a section like this, which always starts with the name of the class and an index, and it always ends with class n. So each of these here, this is a section for one class, this is a section for another class, and all the properties, for example, related to how the model forcing is provided, is then provided here in this section. So here, for example, I provide the file name, which one I want to use, and also some properties like when to start the simulations, etc., etc. And with this, I can customize my model setting in many, many different ways. In this example that you have downloaded, I have made some relevant properties which you as a user are actually encouraged to change in bold red. So for example, now the next thing we want to do is we want to make this a wetland. So what do? So first of all, what I want to do here is I change my tag from bedrock to wetland. So this is mainly that my output files are not simply overwritten. So this will now make output files in here, in the CryoGrid results, that are called ground simple, tea water ice, wetland. So this is really just to distinguish the output files. The second is, well, I have to give it a typical stratigraphy of a wetland. And this is something in CryoGrid you can always just like add lines. So I can just insert a line here. And now I actually want bedrock below 5 meters, not below right at the surface. So I just copy this down here. And then I want an ice content of 0.6, a mineral content of 0.2, and an organic content of 0.2. You can also make this red, that you can see that it has actually been changed. So now I actually have quite some water suddenly between 0 and 5 meters. I'm not changing any of the model physics. So this means with this class ground free water SCB snow, it does not matter if it rains. The sum of the volumetric ice and water contents will always stay the same. But I do one more thing. I'm also not changing my initial temperature profile. I am changing this parameter called surface resistance against evaporation. So you can see default, it is a quite high value, 10,000. So this essentially means there is no water accessible for evapotranspiration at the surface, as it should be for a bedrock surface where all the water runs off. So I will simply set this to 0, because for this stratigraphy, I always have water at the surface. But this is the only changes that I'm actually doing. And then I save it. And I go back. I can just close all of those files. And now I can go back to CryoGrid community run. And I simply clear all my workspace, and I simply run it again, because now ground simple has been changed, and it will make new output files. So I just go to run CG. Once again, I am in CryoGrid, demonstration CryoGrid community run. This is always where I want to run CryoGrid. So I go here, and it now once again makes ground simple, but with changed properties, and you see exactly the same start. And you can let this run. You can always interrupt all of these simulations with Control-C. And we move fast forward now. So now the model has run for 10 years. And when I go back to CryoGrid community results, ground simple, you see that it now also has made this wetland outputs. And I go to the same year, out T water ice. And now I can do the same thing, CryoGrid community run, and then the color plot. So I once again make a color plot for temperature. I make a color plot for ice. And I make a color plot for water. And now we just compare those temperature and color plots. I just make them more visible. So first to the temperature. You can now see that the active layer is a lot shallower. So, and the refreezing takes a lot longer than in the first example. And this is reflected in the ice contents. So you can now see that my ice content to a depth of 5 meters. So I go back here. Told it to a depth of 5 meters. The water plus ice content is supposed to be 0.6. And this is exactly what you see here. The value is 0.6. And the same in the summer. So here my 0.6 is in the summer. The active layer is now just a little bit more than half a meter. And of course, below in the permafrost, there is no water content, because all the water freezes at 0 degrees. So now I have two simulations. I can, for example, now compare the two outputs. So I can go back, results, ground simple, and I can take the same year for the bedrock. So here we have 2010. I can load that. And so now basically the variable has not changed, because the variable is always called, in this case, out T water ice. I can make this plot. Of course, now I've made a mistake. So I have to go to the folder where this is actually located, which is CryoGrid community run. That's where I put them. So CG once again. So this is my color plot. Now I have the two color plots. This is for the wetland, where essentially everything is wet to the surface. The water content is 0.6 in volume, and this would be for bedrock. So here you get an active layer of something like 4.5 meters, as opposed to an active layer of something like 60 centimeters in the case of the wetland. So drastically different results. So now I have prepared another slightly more sophisticated example. So I once again clear my workspace, close all my plots. So now I want to not run the ground simple, but I want to run a slightly more sophisticated example called groundwater balance. So this one is here. It's already made. We'll quickly go back after it has run, and I will tell you what the differences are. But first of all, we have to do the same as always. We have to tell the runcg.m, which is the main file to run the model, which of the parameter files to use. And so far we are using ground simple. So now what we have to do is we have to run groundwater balance. I save it, can go out, and now once again it is run CG. Now you can see here it makes groundwater balance. This is the one that it runs, and now it takes a bit longer. Lookup tables have to be created, etc., etc. So this can take a few seconds, but after this is done, you will see the familiar interface. So here I have used exactly the same output format so that the runs can be compared. So now the runs are starting once again, 1st of September in the year 2000, exactly the same as for the other runs. So this will take a bit longer to run for those 10 years. And you can watch where it has come as soon as it is beyond 1st of September in the year 2010, you have 10 years. So now I just once again interrupted and we go fast forward. So 10 years have been simulated. I clear my workspace to make it all nicer. And so when I go to the results and groundwater balance, I once again see that 10 files have been made. Here the name is groundwater balance, but then it's once again this T, water, and ice. So output variables are for temperature T, water, and ice. And then my tag here in this case has been drained. We'll see in a second why. So drained, I go on this. So you once again see out T, water, ice, and we can exactly use the same commands as before. So I can just do the out T, water, ice, and it makes a color plot. Yeah. In this case, my active layer is a little bit deeper, so something like 80 centimeters. And I can also do the plots for the ice and the water. So here I have both of these. And this looks quite a bit more strange. So a lot is going on here. This is now the ice content. And this is the water content that is being generated. So what's happening here? Well, we see a few things. So first of all, my water content is no longer constant throughout the thawed season. But you can actually see that the water contents change a lot. We have a higher water content right here. So this is basically, I can go back to the temperature. This is where the 0 degree line is located. So you can see that there is some slightly higher water content just above the frozen layer. And the lowest water contents, also very changing, is in the top part of the stratigraphy, so something like the first 20 centimeters or so. And here you can see that the water contents are changing in response. This is simply precipitation events. So here I have actually a water balance. And I have also told it that excess water is supposed to drain. So in principle, it has exactly the same properties as the previous run. So we can have up to 60% water plus ice, which we actually see here. So in the base here, our water plus ice content, oh no, it's actually 0.5, right? So not 0.6. I can show you in the parameter file in a second. So how can we actually understand that? It's even more complicated for the ice contents. Here you, for example, see that there is changes to the ice content even in the winter. So this is this event here. This is, for example, like a snow melt event. So you can see very high water contents here in the middle of November. This is here in the middle of November. And some of this has actually infiltrated into the ground and refrozen, leading to higher ice contents in the active layer. But to understand what was actually happening, we have to go into the parameter file, into the Excel. So for this, we now go here into CryoGrid community results, and then at the water balance, and open the groundwater balance. You see that there's once again, there's a constant file. It's exactly the same as in the previous example. So no changes here. All the changes that have been made are in here. So this is this file groundwater balance. You can see most of it is pretty much the same as before. The same here with the forcing, exactly the same settings as before. Same with the out, exactly the same settings. But here you can now see that in the stratigraphy that we have provided, there are some changes. So once again, we have bedrock below 5 meters. That's exactly cut off in our output files. But above, we have this stratigraphy, which is now in that case 0.5 mineral, and we start with 0.5 water ice. But here you can see that we need 2 additional variables. So I can quickly go back to this one. You saw here, it was just water, ice, mineral, and organic. But here we now suddenly have to tell it some more properties. So this here is the soil type. This is codes. 1 actually means it is something like a coarse grained material, sands. 2 would mean a finer grained material like silts. And I have to tell it a field capacity, which in this case I have set to 0.2. The porosity was 0.5, so the mineral content here is 0.5 as well. So 0.5, half of the pore space can be filled at a maximum with water. And if that water is allowed to drain, it will actually go to the field capacity of 0.2. So is this the only difference? The point is now I have also selected different stratigraphy classes. And this is in here, in this strat classes. Here you can now see that I have not used the class ground free water SEB, which in the previous example was only this one class, ground free water SEB snow. So here below 0 meters, so below the surface, everything was this stratigraphy class. But here I'm now actually selecting 2 different stratigraphy classes on top of each other. So one is this slightly more complicated class, goes from 0 to 2 meters. And then once again, I'm using this simple class ground free water SEB below 2 meter depth. The snow class is exactly the same as in the previous example, this one here. And so this means that my model physics is now completely different in the uppermost 2 meters. And this is what is making all these differences here to the previous example. We'll see why. So what is this class ground freeze K bucket W SEB snow actually doing? So this is a class that actually can represent soil hydrology in a transient way. This is what this bucket W, this stands for a bucket model for water, is actually representing. And the other difference to this, it says here free W, free water. The soil water freezes as free water. Here in this case, there is actually a freeze curve. This is what this freeze C stands for, or a soil freezing characteristics, which can represent, for example, the unfrozen water content in soils at temperatures below 0 degrees, which especially for fine-grained material like the one that I've put in here represents. And we see some implications here. So you can see this is the 0 degree counter line. So it goes to something like, a little bit below, a little bit above 24 meters here. Remember that, and I will go back to the water content, and you can see that there is unfrozen water. This is the water content for a significant depth below this layer. So when I go here, the unfrozen water content is quite low, just something like 0.03%. So not very much, but it is drastically different to the first simulation in Ground Simple that you saw, where the water content here would have been absolutely 0. Same you can see here, 4% and so on. So here the temperatures are below 0. See, same layer below 0, but there is still unfrozen water. And then the second clear implications is when we go to the water balance, you can actually see that the water balance or the soil water is changing in response to some surface forcing. Here in this case, there is some rainfall events in September and October, and here also earlier. At the same time, evapotranspiration is extracted. So in the months where the solar radiation is strongest, around July, I get relatively low water content, something like just 6% in the surface. And this is always volumetric contents. So what is this line here? Well, here you can see, well, my water content is something like 0.2. And this is exactly, the field capacity here. Yeah. So all the water in excess is drained. How do I do that? Well, in CryoGrid, we have the possibility to set lateral interactions with an environment. This is the so-called lateral interaction classes. And here I have selected a class which simulates a seepage phase. So the seepage phase here means that water can seep out basically whenever the ground is unfrozen. And this is what it's actually happening. It goes to the field capacity. If the water content is higher than the field capacity, it will seep out. Well, if it is lower or at the field capacity, there will be no seepage out. And when I go to the plot for the water, this is the reason for this line. Yeah? So all the water that essentially comes from the rainfall will go to the bottom of my active layer and then sort of seep out from there. That's why you have higher water contents here. You can see this is 0.35, 35%, so higher than the 0.2, 20% field capacity. So this is essentially, there's a layer of water which slowly seeps out of my stratigraphy and keeps it relatively dry. So how do I do that in the model? And you can see here that I have this class seepage phase water. You can see here between a lower elevation of 0 meters, so this is far below our surface at 25 meters, and an upper elevation of 25 meters, water can seep out. And this is actually like chosen up here in this class, where I basically tell that the entire model column should lose water in this way through this seepage phase. So here I can actually select these lateral interaction classes. So now the biggest question is, once again, what is happening for the ice content? Why do I have these strange layers here? And well, for this, we actually have to think about our model initialization. What did we tell the model to be the initial state? And I go back here to my stratigraphy. So what we told it is that between 0 and 5 meters, I want the entire ground to be saturated. So water ice has a volumetric content of 0.5, 50%. The remaining part of my space is filled by minerals. So my entire pore space is filled by water. That's my initial state. That is obviously not what is happening here. The water content and the ice contents are much lower. But that's my initial state. And I told it that below 1.5 meters, I want everything to be frozen. So what happens when I now start those simulations? Well, the answer is actually in the out files. So I can go to CryoGrid results. And now I don't open the last file, but I open the first file. This one here. Again, no change. The variable name is the same. But now this is my first year. So I do this one more. Here we go. This is those 3 plots, and they look quite a bit different. So let's look at the temperature plot first. So here you can see that initially I start with my freeze front at 1.5 meters. That is exactly what I've told it here. At 1.5 meters, my ground is changing from unfrozen to frozen. And this is actually now reflected in the water contents. So what you see here is once again up to 1.5 meters. Here, my water content is now very close to 0.5. So you see 0.497, very, very close. But then you can see that, and below the 1.5 meters, it starts to gradually reduce. This is because part of this water is actually ice. So when I go to the ice, it's just the other way around. So there's no ice in this part up to 1.5 meters, and then it gradually starts increasing up to a value of very close to 0.5 here. So at 2 meters, we change to this different class where all the water is actually frozen below 0 degrees. But in that part here, where temperatures are very close to 0, I have, although the temperature is below 0, I have some unfrozen water content, and that means the ice content is not exactly 0. But what happens to my water contents now? And you can see this line is going down, and the values are 0.2. So what happens now here is that initially everything is saturated. I start at 0.5, but then I have applied this lateral boundary condition of a seepage phase. So that means all the water starts to seep out and my water content remains at the field capacity. Here you see an interesting event. I can zoom in. There, some rain is falling at the surface, and you can see that water is infiltrating, raising this water table for a while, but it doesn't really help. Over time, it just reduces. And since I have started at temperatures unfrozen above 0 degrees all the way to 1.5 meters, now you have to remember the active layer after 10 years was only something like 80 centimeters, 0.8 layer. So I had a way too deep active layer. So that means that all the water until 1.5 meter actually has drained. So I have relatively low water contents. And now what happens over time is that my active layer, my seasonal thaw layer, becomes shallower. and some ice is actually forming. So I can once again go to close all, and I go to the second year. So this is the year 2002. I go back to the run, and I once again have those color plots, and I don't make them too big. But here you can see, well, the first ice layer here was formed. This is simply because water is seeping all the way down. You can see here, this is my water. Water has seeped down here around 24 meters, a little bit below, and has started to form ice. So now I actually have quite some ice. This is my first ice layer. And after that time, the active layer is a little bit, make it big, it's a little bit above 24 meters already. So not 1.5 meters depth, but 1 meter depth. And I can do the same for the next year. So I go to 2003. Once again, go back to CryoGrid Community Run. I do that. And you can see another layer, ice layer, sort of water layer has formed. And this has then refrozen here. And this is where the second of those ice layers has been formed. Why does it not infiltrate below this first or the second ice layer? Well, simply because that ice layer becomes impermeable. And then the water does not really go through, but rather pulls up on the surface of it and then freezes down. What is my active layer here? Well, you can see now it's even a bit above 24 meters, and it goes very close to my state after 10 years. I will just bring that back. So I go to the final year that we have simulated. Go back to CryoGrid Community Run. Once again, do these color plots. And here you see the active layer is even a little bit higher. And then in the ice contents, you see the same two lines. This is the ones that have actually formed over time. So with this, you have enough to do for yourself. What you can now do is play a bit with the parameters in those files. So for example, observe what's happening when you change your initialization. So what would happen if I, for example, put my active layer here, not to 1.5 meters, I put it to 0.5 meters. That would will have significant implications. You can introduce another layer. So for example, we could make an organic layer. Simply do insert here, and then we have to go to 0. And then let's say we have a 20 centimeter organic layer that's quite thick. We again start saturated, but we now want a very high porosity, 0.9, no mineral content, and an organic content of 10%. And like these layers tend to be relatively coarse poured, so I put a 1 here. And my field capacity, I want to have this relatively low, so maybe 0.05. So this corresponds to a layer that can get very dry if no water is available. So what would happen in the model simulations? You can also change to a different file name here. So we can go to the Juvasö.mod. I also make this red. Then it would use different forcing data. You could change some parameters like the albedo here. Now it's set to 0.2. Or finally, what you could do here is change the contact length. Now the contact length, so this is basically like I have a model column of 1 times 1 meter, and I have a contact length through which water can seep out. of 1 meter. So it's basically open to one side. I could now make it harder for the water to escape. So just have a contact length of 5 centimeters. So then the water will seep out a lot slower and my water content will all in all be higher. All these changes can be made. You have to save it. I encourage you, you don't have to do this, but it is actually much nicer. Where is it? If in the out class, you give it a tag. So this here, in that case, could be something like not drained, but drained and organic layer. So that will mean that your out files will now, if you run that, not be groundwater balance T-water ice drained, but groundwater balance T-water ice organic layer drained. So then you can distinguish the different runs from each other and make direct comparisons.